Hello, my name is Haoyan, and I'm a second-year graduate student here at University of Florida, majoring in electrical engineering. And this is my final project presentation for my class EEL 6509. And the topic of my project is to investigate a possible way to optimize an uplink NOMA scheme in 5G implementation. The demand for higher data rates and more data has been skyrocketing over the past decade, especially in the year 2020 when the coronavirus situation has had a staggering impact on people's way of life. Many of those activities that involve physical contact have turned virtual and online, including activities like conferencing, socializing, and academic instruction. The demand for online video streaming and video conferencing has never been higher. According to a report released by the International Energy Agency, global internet traffic has seen a 40% surge between February and mid-April. This drastic increase of internet traffic has further made the demand for data access rate much higher. The introduction of 5G has been serving to meet those demands for higher and faster data access on the internet. Since 5G allows for very fast connectivity, high overall throughput, and very low latency connection. However, what access scheme to be used in a 5G implementation remains to be one of the key issues to be discussed in the realm of 5G communication. NOMA, also known as non-orthogonal multiple access, has been the access scheme employed by many 5G system designs. NOMA receives so much attention as it provides the capability of sharing the frequency resources with multiple different users simultaneously. The basic principle behind NOMA is to make use of the superposition coding at the transmitter and apply SIC at the receiver repeatedly. The superposition scheme and the nature of sharing allows NOMA to have the following benefits over the traditional OMA. Higher spectral efficiency due to its ability to allow multiple users to access data at the same time. Lower interference as a result of a repeated SIC at the receiver end, largely increasing the load of served users and support for massive connectivity, and lower latency due to its simultaneity of user access, which cuts the wait time to a trivial amount. And lastly, overall throughput increases due to more effective power allocation scheme. So if NOMA is so good, why don't we just stick with it? Well, despite the tempting benefits a system receives from using NOMA as the communication scheme, there are several downsides to NOMA which can drastically influence the overall stability of the communication and quality of user experience. And one of these downsides is that prior to information decoding, each user needs to decode those of other users who have worse channel gains, which leads to more complexity of the system. And it's more vulnerable towards errors in SIC as one single error in SIC influences all subsequent decoding of other users. Also, drastic gain differences between different users are required for an effective power allocation scheme. And lastly, NOMA is highly sensitive to uncertainty in the measurement of gain. Overall, NOMA is just too complex to be used effectively when it comes to a massive access scenario. In order to lower the complexity introduced by NOMA, the paper that I'm researching on proposes a user pairing algorithm which has the following system design. In the system design, each user represents an uplink multiple access, and G1 through Gn represents the channel gain for each user, and Z is the additive wide Gaussian noise at the receiver. There are two assumptions to note here. The first assumption is that the channel state information is full, and the second assumption is that there is symbol level synchronization to be existent here. Shown here in this particular slide is the actual algorithm written in the form of a pseudocode. The first step comes with a partition. The users are divided into k bins based on their respective transmission power. The number of users in each partition bin cannot exceed 2. Other than the users, the channel resources are also distributed orthogonally into the k channels and into each group. The next step of this algorithm is to make the users who lie in the same group to be transmitting over the subchannels at the same time. The final step involves the actual pairing. All the subchannels become orthogonal and the receiver decodes information transmitted from each subchannel separately. What's also to note here is that the power transmission of each user is sorted in ascending order. Following the sorting, the users are paired and grouped the complexity of the algorithm is highly dependent on the sorting technique employed in the first step. In this case, the algorithm aims to achieve a complexity of O n times log n. For the simulation part, I choose MATLAB as the simulation environment to run the algorithm. I used the code provided by the authors as a starting point and guideline, and made several additions and modifications to better yield the results. The simulation code in MATLAB has the following components: parameter initialization, scenario setup, pure OMA scheme calculation for comparison, and proposed scheme calculation. During the parameter initialization, we make several assumptions. We are assuming the distance parameters to be in the range of 2 to 25 kilometers, the number of users to be 150 in this specific case. Other parameters like N0, L1, and L2 are all initialized in this step. Thus, power is calculated using those parameters. The scenario setup step corresponds to the very first step of the algorithm described in the previous slide, which is to divide the users into individual groups based on the equivalent power transmitted from each user, and each group size does not exceed 2. The OMA calculation step calculates the throughput of the scenario using orthogonal multiple access method to serve as the comparison with the proposed algorithm, which will be calculated in the next step. This step is the final step that calculates the throughput of the same scenario using the proposed scheme of user pairing and combination of OMA and NOMA. The figure shown here in this slide shows a plot with the throughput calculations of both the OMA and the proposed user pairing scheme overlaid for comparison. The horizontal axis represents the number of users, while the vertical axis represents the system throughput in units of bits over symbol. By observation of the output plot the throughput achieved by the proposed scheme and the conventional OMA scheme, the overall throughput of the proposed scheme is greater than that of the OMA scheme. The difference between these two schemes in terms of throughput decreases as the number of users increases, while maintaining greater than 0. However, my result has some differences than the theoretical output generated by the authors of the paper that I'm researching on. This particular figure shown here shows the theoretical throughput calculated in the author's simulation. Comparing the results from the figure shown in the last slide, it is observed that the overall trend of both of these two plots is the same, which is that the proposed scheme is more optimal than the OMA scheme as it increases the throughput of the system regardless of the number of users in the system. However, the theoretical plot shows that as the number of users increases, the throughput difference between the two schemes are enlarged, while the other figure shows the opposite. So what could possibly be the reasons behind such differences between my simulated result and the theoretical result? Well, my guess is that, first of all, the number of users that are simulated in those two cases are different. In my particular simulation, the user number up to 140 are considered, which is a much bigger scale compared with the scale considered for the simulation in the author's case. In the author's case, only a user number up to 18 is considered. There might be other factors which can influence the overall result, including different parameter setups, different power calculations, or scenario setups. Any slight differences can cause the results to vary. So as a quick sum up, in this project, I've been able to identify a problem for a massive user access scheme. I've been able to use an algorithm proposed by a bunch of other researchers working in this area to actually simplify the complexity of a NOMA access scheme while maintaining the throughput at a high level to support those users in large numbers. I've been able to simulate this particular algorithm in MATLAB with some pre-assumed parameters to set up the context of the simulation. And finally, I was able to run the simulation to get both the results and the calculations for the proposed algorithm and the conventional OMA calculation for comparison. So in conclusion, I've been able to simulate an algorithm to solve a problem through the course of this project. I have encountered some interesting findings while researching works of other scholars working on similar problems. I've also found that despite using the exact same procedures for algorithms, there are many other factors which can drastically influence the output of the simulation. But fortunately, my simulation achieves something consistent of my expectations. That's it for my presentation. Thank you for listening.